Okay, so what we want to do is get some notation going here to solve this blood testing problem. So I'm going to use POS to be positive, and I'm going to use N to be negative. And the first thing that I see is that the probability of testing positive is equal to 0.015. So if that's the probability of testing positive, then the probability of testing negative, its complement, right, is going to look like 1 minus 0.015. And the probability of being negative, therefore, would be probability of being 0.985. That's the complement. So now with those defined, let's turn in terms of what the notation we have going on here, let's get the probability that we want defined. So our probability is that if we combine all 5, that we will get a positive result. So a positive result means that the probability that in 5 at least 1 is positive, right? So if I consider x to be a random variable, meaning the number of positive results in 5 samples, then I can rewrite this in terms of something that looks a little nicer than what I've got going on there. So the probability that my random variable x is at least 1, right? So the number of positive in 5 samples is greater than or equal to 1. So this one is the probability that I want to find. However, that would be the probability that exactly 1 is positive, or that exactly 2 is positive, or exactly 3 is positive, or exactly 4 is positive, or exactly 5 is positive. And in terms of finding all those probabilities, that can be quite difficult. So let's take a different tact on this. Let's say that we can find this probability of being at least 1 more easily by looking at it in terms of the complement, the probability of being fewer than 1. And then we're going to turn around and we're going to say, well, what does this really mean? Fewer than 1 really means none are positive, right? So if you have fewer than 1 positive, that means none of them are positive. And what does it really mean to have none of them positive? Well, having none of them positive is really meaning that all of them are negative, right? So we're going to change this around in step 3 from being about being positive to about being negative. And now you see why I got the complements in the first place. So the probability here of x being greater than or equal to 1, I'm now going to put in terms of 1 minus the probability that we have a negative 1 5 times. So this is the probability that the first one is negative, and the second one is negative, and the third one is negative, and the fourth one is negative, and the fifth one is negative. And those are all independent events, right? Because they're independent people, they're all separate people. One's probability doesn't depend upon another one. And so this goes back to that repeated probabilities we were talking about in the last section. And so this is going to end up looking like 1 minus, and then the probability of being a negative raised to the 5th power. And if we take a look at that probability, then I'm going to use a scientific calculator here. So I'm going to pause while I go get the scientific calculator, and I'm going to use one off the internet. So just give me a second here, and it's going to look pretty transparent to you. Okay, so here's a scientific calculator that I'm using off the internet. So what I want is 0.9, oops, didn't get the decimal there, 0.985 raised to the 5th power. And that gives me 0.927265 approximately, and then I'm going to do this as 1 minus that value. So I'm going to change the sign of it to negative, and then I'm going to add 1, because that's the same as doing 1 minus that value. And that equals, and there's my value. So this value is 0.0278, and so I'm going to round this to 728. So my probability here looks like approximately 0.072 and 8. So in other words, the probability that having at least one of them negative is going to be about a 7.3% chance that they're all going to be, or that there's one or more of them that are positive. And so what really this is all about is, this is really all about telling you that, hey, if you've got a probability going on here that has only about a 7.3% chance of happening, then it's perfectly okay to group all of these samples together, because it's going to be a rare occurrence that you're going to have to retest to then find out which one is actually the one that has a positive value. So you're going to save your lab time and money in order to just throw these all together. And very rarely are you going to have to go back and retest, because it's a rare occurrence, 7.3% chance, that you're going to run across a case where you actually have to go retest all 5 of them. And if you ran across a case where you did get a positive, then you're going to have to go test all 5 of them, because you don't know if it is the 1 or the 2 or the 3 or the 4 or all 5 of them that are creating this thing being positive. And just because you ran across one that was a positive value wouldn't preclude that another one would be positive, or another one, or another one, in other words. So you'd have to test them all. So anyway, that is how we use our ideas of complements and combine that with the probability of a repeated event in order to get more complex probabilities. All right, let's go on to our next example in our notes here. And this one is, a student experiences difficulties with a malfunctioning alarm clock. And this student decides, hey, instead of 1 alarm, I'm going to use 3. And that way I don't have to be late for my exam or whatever. And this problem is exactly the same thing as before. These are problems that are known as redundancy problems. So instead of using 1 alarm, he uses 3, and the probability that at least one works if an individual has a 0.98 chance of working. So if we say that it works, the probability of that working we have going on, and this is going to end up being just like that last problem that we worked. So the probability of working is equal to 0.98, and then the not working here is going to be the complement of that. So the probability of not working is 1 minus the probability of it working, which is equal to 1 minus 0.98. So we have a probability of 0.02 in terms of it not working. So we want to define the probability of it at least, so we can use what we know. So the probability of at least one working, right? At least one working alarm means he's going to get up on time, right? That's what we want to know. So let's say X is the event that the number of working ones in 3. So this event, or this probability, is the probability that X is greater than or equal to 1. That's the at least one work. And so now we're going to redefine that as 1 minus the probability of X being less than 1. And less than 1, of course, again, just the same thing as we did before, less than 1 really means that this is none work. And this means, of course, that we have all of them not working. So this is equal to the probability of, 1 minus the probability that none work. So, this is the probability of not working cubed, because we have 3 alarm clocks, right? And the first one doesn't work, and the second one doesn't work, and the third one doesn't work. So this is going to look like 1 minus 0.02, and then that gets cubed. And this is going to look like 1 minus point, and then this is going to be 0, 0, 0, 0, 0, and an 8 there, right? 2 cubed is 8, and 2 decimals, 2 decimals, and 2 decimals, that makes 6. So there's 2, 4, and 6, and that'd be my probability. And this, of course, gives me point, and this is 9, 9, 9, 9, 9, 2. And that would be the probability that I'm going to, or the student is going to get woken up if they use 3 alarms. The probability is so high that if the student said, "Hey, professor, I missed my test today because guess what? I used 3 alarms and all 3 of them didn't go off." You're going to go, "Really? You have a probability of 0.00008 that that all 3 don't work and you don't get up to go out to test on time?" So you have a 99.9992 chance of getting here if you use 3 alarms. Very, very suspicious, right? It's a very, very odd occurrence. So that is our probability that we're looking at in that case. Exactly the same thing as the blood test case. Now let's talk about conditional probability rule from that point. And what I would like to do here is I'd like to go ahead and break the videos and start afresh for this conditional probability rule. And as you see, we're going to be working with our contingency tables, our two-way tables again.